Hello, Ryan here from RLF Vacuum Cleaners and They Can Live. And in today's video we're going to be talking about this STC1000 temperature controller. I'll give you a quick show of the wiring diagram. This is 110 to 220 volt AC, your power supply, temperature sensor, and then you have your two relays for heating and cooling. But it's not actually the device I want to look at, it's the circuitry inside, which is actually the clever and interesting bit that I want to show you. So, note this 110 to 220 volt AC, which means it's got some sort of switch mode power supply in it. But it doesn't actually weigh anything. So it can't have any sort of lots of circuitry in it because it doesn't actually weigh anything. So what I've done was, I opened it up, and I'll do this in a minute, and I'll explain what was inside. I am back in. What I've done is I've removed the circuit board from its case, like so. On the top side you can see it's a very minimalist design. You've got two relays here for the outputs, a couple of capacitors and an inductor. Looks fairly minimalist, and you've got your power in here. But on this side you've got quite a few components, diodes and resistors, etc. But it's this particular chip here. If I can get the camera in here to zoom in. This, the LP2188 chip. That's actually the cleverness of this whole entire circuit board. This here is a non-isolated AC to DC converter. Very, very simply, what this does is, this does all your power stuff to take your mains voltage and outputs a 5 volt DC supply, which powers the control board, the 7-segment display and the relays. And it does this, the chip does all the complicated stuff, you then just have a few auxiliary components to support it. So power comes in, goes through these two diodes to a capacitor. That capacitor then goes to the chip, which then does its cleverness, and then that outputs a 5 volt non-isolated DC supply. And then you have your negative supply here, which then goes down to here. Anything to worry is the negative of the 5 volt and the neutral of the 240 volt are actually common together. That's where your non-isolation bit comes from. So literally that's all it is. And then you literally have your capacitor on your inlet. You have your capacitor there. You have a capacitor on your outlet. You have an inductor on the outlet. Couple that with a few little resistors. This bit here is all for the relay switching, and then on the front you've got a couple of buttons and 7-segment display, and then underneath the 7-segment display you've got your controller, and that is it. This particular controller I bought off eBay for £8.50 including delivery, and you can see for £8.50, that's a bit that really surprised me, because usually these temperature controllers are usually quite expensive. Some of the cheaper ones are your sort of 15-20 quid. If you go for a proper brand name one from a manufacturer, you're talking hundreds of pounds. And for a long time I thought one of these chips possible, but I never could find what I wanted anywhere online. Again, these chips they're quite niche. They're for low power, low current applications. This particular chip only has a 200 milliamp current output, which again is very piddly. But then again, for something like this, a 7-segment display uses bugger all. Your only real current draw is going to be from your relays. They're probably going to draw, I don't know, 70-80 milliamps each. But then again, you're not going to have two relays running at each time. 7-segment display, microcontroller. You're probably going to be talking about maybe most of the segments lit. You're probably going to be looking at maybe 1 or 2 milliamps per segment. So realistically, you're not going to be talking more than sort of 25-30 milliamp, including the controller. So realistically, if you've got the relay on, drawing current, you're not going to be drawing more than 100 milliamps of current. But this is the clever design. Obviously, somebody in China has read a data sheet somewhere, read some sort of manual or something, and they've come up with, yes, this chip here you can buy these in bulk for about 30p online. So if I can buy them for 30p in bulks of 10, imagine if you were mass producing something like this in the thousands. You're talking pence. You're probably talking the whole board and everything. Probably looking about £1.50 for the whole entire components for this board. Which again, it's clever engineering. And now I've discovered this chip, all you need is diodes, capacitors, a few resistors, or a resistor and inductors. I mean, I could implement this into lots of designs, and this is all because I was brave enough to buy a cheap Chinese piece of technology. As you can see, this one's actually very well implemented. You've got the anti-tracking cut out there. I'd say that's pretty good design. Obviously, longevity, there's very little information about this chip online, but you can buy them. How long they last, a different question. Again, this is one of the reasons why I come across buy these things, to test these things out. But again, these things prove to be ultra reliable. You can build even smaller circuit boards for small things, so like your Raspberry Pi and your Pico microcontroller stuff. If you can get your 5 volts and you don't have anything too current drawing, you can make this into a mains powered system instead of having to plug it into USB or anything like that. So yeah, this is the sort of clever design that I like, and I'm going to actually implement some of these designs. I'm going to get some of these chips and some circuit boards, you know, with capacitors and inductors, and I'm going to build a few of these circuits and I'm going to test them out. Obviously things like EMC and interference and things like that, not quite sure what they are. I'm guessing this one's probably a bit lacking. Well, it might be alright actually. Got inductor, capacitor, yeah. I reckon interference probably going to be very minimal, but we'll test that. So yeah, buying cheap things off eBay isn't always bad as long as you know what you're looking at. And again, this is something I've been looking for a long time. AC to DC converter, covers a wide range of voltages, and it's mega cheap. So yeah, one of the things I quickly want to test is to make sure that the isolation on the exposed metal temperature probe is actually isolated enough that isn't going to cause a shock risk. So what we're going to do is, we've got it connected to our Cliff quick test. I'm going to turn that on, like so. So we can put one probe onto ground and the other onto the probe, and we're going to see what reading we're going to get. So onto ground, and you can see we're getting about 1.5, 1.6 volts. Let's see if we can get a bit. Oh, we're getting good connection. We're getting about 3 volts, which again, it's nothing really. So yeah, I consider the isolation on that pretty good. I've got it running on, what's the voltage here, about 237 volts. No magic smokes coming out. Everything seems to be working as it should. One of the things I wanted to check was, could you actually run this controller off a low voltage DC supply? Now, although this is rated 110 volt to 220 volt AC, what would happen if you ran it on a low voltage DC supply? Now, because of the way the rectification works on this, it's just 2 diodes, which gives you puny single half wave rectification. If you get the polarity correct, you could run it on DC, but the only problem was, instead of getting power every half wave, you just get one continuous DC supply. And we've got it connected up to our old Dyson charger, which we use to power stuff, like this. We'll check the voltage. I think it's, these DC chargers actually have split voltages on them. You can have 24 and I think it's 18 volts. So we've got that connected up to 18 volts. So that's running on 18 volts DC. Not a problem. It doesn't seem to be getting hot or anything like that. We had this running for a little while. It works just as it would normally. So what I'll do is we'll hold the sensor. You see the temperature go up. I'm not quite sure what it's set at, but at some point you can turn the relay. It could run on the heater relay at the moment. At some point it will turn the heater relay off, and if hopefully it's soon enough, we should be able to get the cool relay to come on. Again, this is just running on 18 volt DC, so not quite sure how that chip would handle not having half-wave rectification, but then again the voltage is a lot lower. So again, this shouldn't be a problem because all the capacitors in there are rated for main voltage, so it was obviously set to something quite ridiculous, so we'll turn the temperature down. Right, changing the temperature on these because it's a bit fiddly actually. So what you want to do is you want to press the S button. Oh, press and hold the S button. Is it F1 we want? Oops, wrong button. F1, yes. And then you press and hold the two buttons, they're set to 37. But you've got to do it quickly, otherwise it comes out. So you're on F1, yes. Both buttons, drop it. So you can see it's gone to cool now. So I've got that set to 28 degrees or whatever. So if we hold that. Again, with these you can set the offset as well, set the offset on them as well. So they have like a little period in the middle where they're off. Which is press and hold F1, F4. The offset temperature. No, that's the adjustment for the NTC sensor. So it must be F3 we want. Is that one? Or is that F2? Ah yeah, that's the offset. So you set the offset to 4 degrees. Whoop. Again, this is a bit fiddly trying to do one-handed. You can see the cool light's flashing to say that it's timed out. But yeah, that's how you set it. I'll change the things on there. Press S. F1 is your temperature. F4 is the temperature offset if you want to find the temperature sensors a bit out. F3 is the time delay. F2 is the offset. So which means it'll go up and down 1.6 degrees before it does anything. So yeah, I thought I'd just add that on to the end in case anybody wants to use one of these STC1000 sensors. So yeah, thank you very much for watching and goodbye.